Hello everyone, welcome to our presentations of Neighbor 8 Privacy by Design Home Services. This project was developed as part of a secure software engineering course to demonstrate how security and usability can be built together from one day. Our system includes 4 models: Group A, B, C, D. The main goal of our system is to protect users' privacy and ensure accountability, following the principles of privacy by design and zero trust architecture. Every action is verified, logged, and encrypted. Even the backend never sees plain text data. About our security's privacy requirements, um, let's show our requirements and objective and responsible group. Neighbor 8 is a community's collaboration platform that connected neighbors who need help with those who can provide assistance, such as home repair, deliveries, of simple daily tasks. Group A: Authentication and Trust. These models secure how users access our platform. We implemented JWT-based login, so after authentications, the server issues a signed token that presents and the user's identity. Every request carries this token for verification, ensure seamless, privacy-preserving communication. We also use rule-based access control. Users can be helpers, requesters, or administrators. All API endpoints are protected by Spring Secure filters. Many unauthorized access attempts return for those 3 forbidden. This design aligns with OWASP ASVS standards for identity and access control. Group B: Tasks and Machine. Once users log in, they can create or accept service tasks. Each task has an owner and optionally a helper. The key issue we solved was integrity. Only the assigned members can modify or view their tasks. This is enforced by our access policies asserters member method, which checks if the requester's ID matches the task participants. The task lifecycle goes from open, assigned, completed. Each state transitions, triggers, and audit log entire from traceability. By Group A and Group B, we ensure that tasks are both authenticated and authorized before any data access happens. Now, my teammates will introduce Group C and D, which focus on secure communications.
Group C implements end-to-end encrypted messaging and a panic alert mechanism. Users can communicate securely about ongoing tasks. Before messages are sent, the front end performs AES encryption locally. The backend receives only several texts and stores it in H2 in-memory database, which clears itself once the system shuts down, ensuring privacy by default. On the backend, the message service verifies user's token, confirms task membership, and logs each message event in the audit service. We also developed a panic button, which immediately records an emergency alert as a panic.event in the audit log for admin review. These satisfy 2 key privacy requirements: CR1 ciphertext only message storage, CR2 member-only messages access. Group D ensures the system transparency and accountability. We implemented HTTPS content security policy and referral policy headers to prevent data interception. All critical operations, login, task creation, message sending, panic events, are logged with anonymized user IDs. Logs are automatically deleted after 7 days by a retention job, protecting long-term privacy. We also verified compliance with ISO IEC 27001 controls for data protection and OWASP ASVS login requirements. Together, Group C and D create a source communication pipeline. Every message, every action, every request is both private and traceable.
Thank you. As the integration coordinator, I combined all models, articulate tasks, messaging, and audit into a single rainbow system. We built a multi-modal Maven project where each service communicates through RESET APIs. GWT tokens flow across all components, ensuring a unified identity model. The front-end was built in React plus TypeScript, communicating securely with the Springboard backend via HTTPS. We used a unified HDE memory database, which provides volatile storage and ensures no personal data persists after shutdown. Integration challenges we overcome include token validation between models, inconsistent message encoding, and dependence conflicts. By centralized configurations in security config and standardizing DTOS, we achieved seamless model communication. Now we will demonstrate the neighbor-aid prototype to show these functionalities live.
Hello everyone, this is neighbor-aid, a small privacy mind platform for neighborhoods to post and accept tasks. I will work through the whole flow and along the way, point out the security control we built in. We start in login in user 1 at example.com and the password is pass. Look, now we can see the backward return GWT access token. Every API can use this token, and if we use some other users, like someone not single in the database, it will be return false and get the state 401. Okay, let us switch to user 1. And then, as user 1, I will create a task by milk, and the area is 5,000 and 2 bottles. Create the response. It can see it's okay, it's true, and the state is 200, and the title and the date, title, area, postcode, ID, state, and the data is open. We can also check it in here. But the same user can't both post and accept the same task, so we enforce the role separation to avoid conflict. Like here, we can see the ID is 1. If you try to use user 1 to accept this task, it will be false and the state is 401. Now we try to switch to user 2, login, we get to another unique access token. Now we can try to use user 2 to accept the task. Okay, that's true, and the state is 200. We can select, you see the state change to assigned from open. Now, with the task assigned, both members can chat. I will send arriving 2 minutes later, but before it, we can see if someone tries to send a message with a bad or umpire session, the request will reject right away. Like here, we say, I arrive 2 minutes later. It will reject false and reject it. And the data is 401. But if I use this ID, this is the right ID. Connect user 1 and user 2 here, and I create the session and send it again. You can see it's great. It's right, and it has been success. And we can see it. We can see the task at here. I arrived 2 minutes later. And now let's pop into the H2 console. It's a in-memory database. We connect, and we can see the message here. I sent just now, arrived 2 minutes later. Here, and we can also validate session ownership. If a user password run a wrong task ID or try to create a session for a task they're not part of, the bank reject it. Like here, create, they will reject it. And the panic action for emergency when I trigger it, the pen for write audio recorder. Here, audio recorders. What we do just now, the session create, the message send. That's all. Okay, let's query the audience table in H2. Clear it, the audience, run it. Okay, we can see the order here, and we use the UID hash to that provide traceability without exposing identities. It's privacy proving oriented. Finally, and we can use this run retention now, but this only clean the message about 7 days ago. So we can see it at the same way. You can see the message here under the audience. Okay, that's a purge task. Finally, our demo using an in-memory H2 database. When I stop the app and refresh the H2 console, the tables are gone. We can refresh it. Now we go to the web again, connect, and we'll try to select the message. Nothing here. Okay, thank you for listening.